In this video, we're going to analyze the dynamic behavior of our simplest amplifier, the common emitter. That means we'll try to guess what its Bode plot looks like based on circuit analysis. And it might be tempting to do that just by finding the transfer function for this circuit, and if that works, maybe we can do that for all of our circuits. This video is a motivation to not do that. We're going to find out that the common emitter transfer function is very complicated, so we'll start looking for ways to simplify it next. I've drawn a common emitter on the left here, and I've put its dynamic small signal model in the center of the slide. I took an unusual step when I made the small signal model, which was converting the input voltage source here to an input current source here, so that's a Norton equivalent. This just saves us a bit of algebra. And specifically, it saves it here, where we set up the problem by writing two nodal equations. This equation balances the current at the base node, so IN is equal to the voltage out through the cap and R pi and C mu. And this equation balances the current at the collector. You can see that these are two variables and two unknowns, so surely simplifying these will be straightforward and quick, and it'll yield a super tractable expression. So, just a little bit of algebra happens and we get this monstrosity. This expression is completely accurate, so it's good that we have it around as a point of comparison for our approximations. However, this is complicated enough that it's almost unusable, so don't worry about memorizing it. Do notice, however, that we have a second order system. There's an s squared term and an s term, and that it has a right half plane 0 in the numerator. So this is given by a 1 minus s over z, so that's a 0 located at gm over c mu. We can simplify this expression with a few highly accurate assumptions. We start by breaking the transfer function down. We can see that we have a right half plane 0 on top of the expression, and we'll find out later that that 0 turns out to be quite bad for stability, but we'll deal with it later too. We can also see that we have two poles, the s squared and the s here. Those two poles are real. One way you can justify this is that you've never seen an amplifier have a ringing step response in class. So that means we can write our denominator polynomial as d of s is equal to tau 1s plus 1 times tau 2s plus 1. So just the product of two first order real terms. Multiplying that out gives us this second order expression. The next thing to note is that these two poles are widely separated. So one is very dominant. Tau 1 is much larger than tau 2, or equivalently, the first pole is at a much lower frequency than the second pole. We're just asserting this for now, but we can check it at the end of the slide. With this assumption, we can rewrite our expression for the denominator. And in particular, we notice that this term that used to be tau 1 plus tau 2 has just turned into tau 1. So that means we can grab our first order time constant just by pulling off the coefficient in front of the s term here. We do that, and we can almost just stop here. We know our 3 dB frequency is going to be set by this pole because it's much slower than the other pole in the system. So we generally care most about having a good estimate of this tau 1 for bandwidth estimation purposes. That's one of our major goals in analyzing the dynamics of amplifiers. However, higher order poles can matter a lot for stability, so we'll soldier on for a bit. We can find our second pole location by taking the ratio of this tau 1, tau 2 coefficient, so everything in front of s squared, against tau 1. We can see that our assumption of wide separation is correct by focusing on this GM RC term in the bottom here. GM times RC is the voltage gain of our amplifier, so we expect this term to be quite big, which means overall tau 2 is going to be a small ratio, or determined by a small ratio of normal cap that we've seen before. So this is all great, and we do have some slightly simpler expressions now, but this is still hard to use in the lab. One thing that's particularly frustrating is both tau1 and tau2 depend on both cpi and cmu, so we can't use our trick of Thevenizing from one cap to calculate time constants quickly. And that's an important detail. In general, when you're doing dynamic analysis, it's tempting to associate each cap with a pole, but that approach falls apart in complicated circuits. So, in summary, the common emitter has a complicated transfer function, which I've copied here just to convince you, not because you need to remember it. The common emitter has two real widely spaced poles and one right half plane 0, and here are the two pole locations if you care. The poles aren't associated with specific capacitors, and this approach is unsustainable. We need faster, lab-suitable bandwidth estimation.